Hello, beautiful life forms of the internet. It is I, your favorite cyborg, Dead Program, along with my favorite companion, cyborg Gopherbot, half gopher, half robot. We're not even sure which half is which. But here we are again with you at beautiful La Pipa in Asturias, España. And today we're going to do some very cool, interesting, fun things I've been planning all week long for this very moment. Yes. So pay no attention to the face behind the curtain. Uh-oh. What have we done? Yes, we're back. Okay. So, Gopherbot, just hang out for a minute because I have work for you today. So we have, as usual, we have to talk about some of the news of the week. Once again,
with the horizon of planet Earth.
we have more SpaceX launches of Starlink satellites. I mean, these humans never stop.
Turning away with the horizon of
It's incredible. It's literally 60 satellites a week. How they keep this up, it's amazing. It's pretty exciting. And I really need this throughput. So send me my dish, would you? So in closer to terrestrial concerns, my friends over at Google Cloud have been working on some very, very interesting things, and they've just announced it this week, I believe yesterday. So now we can talk about it. How carbon-free is your cloud? So Google, providing cloud services, would like to be able to answer the question, with your data center that you're using for your cloud-based processing, how about the sources of energy? So the Google Cloud Platform has mapped all of their data centers throughout planet Earth and has mapped them for what type of energy is being used to power that particular data center. You know, is it fully renewable or maybe, well, not so much? So very cool map. You can check this out. They've been publishing this data, and you can check this out in real time. Turns out that the technology they're using is coming from a very interesting company called Tomorrow. So Tomorrow provides data tools for carbon utilization for different computational scenarios, let us say. So they have a very interesting map called Electricity Map, and I was checking this out at electricitymap.org, and what this shows us is it actually shows us the intensity of the climate impact for all of the zones on the planet where they're able to get this data. So once again, here's a real life application of the Internet of Things, this time tied to real-time energy production and consumption in this oh so important area of electricity. Yes, electricity. Our whole civilization needs it. We need to electrify, and we need to do it now. All right, so that was fun, cool, and interesting things that we need to do now, really, no joke. We're going to do some more things about renewable technologies and ways that we can apply some of the interesting robotics, drones, and connected sensors to some real-world applications. All right, so last week we started where's my mask? A cool new feature with my friend Lorenzo called Learning to Tiny Go. Learning to Tiny Go. Go, go, go. Lorenzo.
Hello.
How you doing, man?
I'm fine, thank you.
Yeah, thanks for coming back. I didn't scare you away yet because of...
for inviting me again.
Yes, well, today I think I'm more prepared. I've brought a few items to replace the items from last week. Here, let's switch over to the table camera so we can take a look. So I brought a functional, actually, let's go to the micro. I brought a functional Arduino Nano 33 IoT board that has the headers already soldered on. It is on a black breadboard. And it even has the stickers included, so you get that. And then I also brought you the kit. Let's switch over to the table view. So the kit is the kit of parts that you get to, here, I'll move over this way. So this is the kit of parts that comes all together for the information for this workshop for learning how to program your microcontroller
Beautiful.
using TinyGo.
Can I?
Yeah, you definitely take it out, and let's hope that, in fact, all of the pieces are there.
Beautiful.
I guess we'll find out.
Yeah, there are many sensors I see. Grove touch, light sensor,
Light
LED,
sensor, LEDs,
and we have here button,
button,
and this is a potentiometer,
yes.
rotary encoder, or no, rotary angle sensor.
So
apparently.
yes, a potentiometer or
Yeah.
variable resistor,
And this sound sensor,
a sound sensor.
a nice OLED display.
Yeah, here, let's take a closer look
I
at
love
that.
this one.
Oh yeah, I mean, you can never go wrong with these little displays, right? And this one is really, really small.
Vibration sensor, and wow, temperature, another LED, and what do we have here? I think it's a buzzer, yes, and 3-axis accelerometer, and nothing. That's more than enough, I guess.
Yeah, that's probably, I feel like we're missing a few cables. No, I think we got them all. So yeah, this, when we are done,
Yes.
after all of the weeks, you will have been able to put all of these parts together into a single functioning unit
Are you
using
sure I will
TinyGo.
be able to do that?
I'm pretty sure.
I hope so. That will be fantastic.
So let's take a look at the information here again.
We can apply the 1% rule, the compound interest. Maybe I learned something out of that.
Hopefully so.
With all these tiny pieces.
So we have here the microcontroller, which,
Okay.
if you remember from last time, because the silk screen is on the back side of the board, we had to create this image with all of the pins labeled. That way it's a little easier, because otherwise it's very hard to do.
Yes.
And they just couldn't fit the silk screen because there's so many surface mount components on the front side.
Yeah.
They just couldn't fit all of the writing, basically.
Yeah. The idea is to keep this one printed on your wall and.
Yeah, or just keep it open in a
At
separate
least for a
window.
while.
That's what I do. So, what operating system do you usually use?
For work, I'm on a Windows operating system.
Mm-hmm.
I usually develop onto a Raspberry Pi, and also sometimes I used to have a Mac, and so more or less, but I'm not using it. It's been a while now.
Well, the Raspberry Pi is a very small Linux computer. It works quite well to use for, I mean, you can also use Windows and you can use a Mac, because we have support in TinyGo for all of these platforms.
Great.
So if you go to the website, which actually I will show you a little peek of our new TinyGo website.
Oh, fantastic.
Yes, we
This is recent, because I think the last week it wasn't up.
well, this is not still up. This is the new website
Okay.
that is going to be coming out at the same time as the new TinyGo release next week.
Great stuff.
So this information for the microcontroller board that we're looking at, which is the Arduino IoT, or Arduino Nano 33 IoT board, you can find the same information here. Oh, we have a broken image link. Got to fix that. But this will tell you the things you need to know in order to install the flashing tool because the Arduino Nano 33 uses a bootloader called BOSAC. And the BOSAC bootloader requires this BOSA tool. So there is a Windows version, there is a Linux version, and there's a Mac OS version. So it's very basic to install.
Does the Linux version work for a Raspberry?
Yes.
Okay.
Yes. So you can install from source and build it on Raspbian, and then it'll probably look very much like what we are going to do here today. So last time the problem we ran into was we were trying to do step 0,
Yes.
right? So step 0 is that we're just going to flash the code to blink the built-in LED.
Okay.
And in order to do that, we're going to flash it with this code. So let's go take a look at the code. Let's see.
So, yeah, of course, the BOSA is already there.
Yes, I've already installed these things a while ago. So if we go and we take a look under Sensor, Arduino, Step 0, here we can see the code. And we looked at this last week, but we should go over it again because it's been a long week.
Okay.
So the first line we have this is package main.
If I'm not wrong, package is just defines the script we are using, correct?
So a package is a group of code that is collected together because it shares some like functionality. So package main means it's the main package that we're going to use for our program. So it's the starting point.
Okay. Does it have to be the same as the file name then?
No, we can actually have several different files which will all get combined together. If they're all in package main, then the Go compiler will take that and compile them all together into the single package.
Okay, I see.
So then we have import, which is very much like the Python import statement that you've used so many times.
So machine is, I guess, the one that allows to flash, to communicate with the microcontroller we have on the various platforms.
Yeah, that's the hardware abstraction layer
The hardware abstraction
that
layer.
TinyGo provides.
And time, maybe it's the same. I mean, the Go time library, that's correct?
That's right. It's the standard Go time package.
Okay.
And then we have our function main.
I see. Okay.
So first we say LED equals machine.led.
So LED just identifies the integrated LED.
So yeah, in this case, the left-hand side is the name of the variable. And then equals in Go is very similar to the equals operator in the Pascal programming language, which is where they drew it from. It both defines the variable and it assigns it a value all in one step.
It infers the type, I guess, as well.
Exactly. It's able to infer the type by looking at machine.led, which machine.led is of type pin. And so that's the built-in LED on any given machine. Like if a board has a built-in LED, it'll always be machine.led.
Okay.
That way this same program can run on many different boards and it will basically do the same thing. So the first thing it's going to do is it needs to configure, it says led.configure to configure that pin. And it configures it using, in Go, what's called a structure. A structure in Go is like a structure in C or a struct. What's it called in Python when you have an object?
Well, you define it with init and a class.
A class,
Yes,
basically.
a class. Yeah.
So even though it doesn't have any inheritance, but in Go, we do not have inheritance, we do have typing. So if a type, in this case, the pin type has a configure method on it, then even if this pin is of a different kind of machine, we could still call this same function
Yes.
because it defines this function as part of its interface of saying all pins support certain functions. One of them is to configure it, that way it's ready to go, in this case, as an output pin.
Okay.
Because we have to decide, is the pin going to be an input or is it going to be an output?
I see.
And then in Go, there's only one looping construct. It's for. In Python, you have for loops,
Why?
and you have while loops, and you have do until. In Go, you only have one thing, and that is for. And if we say for with no parameter, it just means forever. It's the same as while true. So then our LED.low turns that LED and it makes it
State.
off, exactly. So then we call the go time sleep function, which goes to sleep, and then we pass that how long we want it to sleep for. So in this case, it's 500 milliseconds. And so in Go, because time duration is a type, we have to say the type times however many of that type we want. So if it's milliseconds times 500, it's 500 milliseconds.
Okay.
And then we turn the pin high, turning it on, and then we sleep for another 500 milliseconds. And we just repeat this
forever.
over and over forever. So if we take the cable
Okay.
and we plug it into the USB port on,
Here we have it. La la. It's blinking.
it's already blinking because I had already,
It was already flashed.
yes, I cheated. So we'll go over to my terminal here, and let's see what version of Go I have. And let's see, sorry, Go version. I'm going to increase the size of my font a little here. Go version tells us, oh, there we go. So Go version, tells us what version of Go is installed. And if I say TinyGo version, this will tell us what version of TinyGo is installed. In this case, it's a development version.
Is it querying the?
No,
okay.
it's the we haven't put any code on the board yet.
Okay.
In theory, this is the compiler that I have on my computer, and it's using Go 1.16.3, and it's using LLVM 11. So TinyGo is a compiler that gets its work done by using two tools, using the Go compiler itself. Since Go is written in Go, the Go compiler is written in Go.
Okay.
And so we can reuse parts of the Go compiler. And then we combine that with LLVM, which is a compiler that is used to compile the Swift programming language. It's used to compile Rust.
Okay.
You know, it's used in C++ and C. You know, it's a compiler that supports many different languages and platforms. It's really a framework for creating compilers and languages, right? So we've got TinyGo installed. And so then I have, one thing that I do not have in this project is what's known as a modules file. So in Go, the way that we determine whether we have any dependencies, any packages that we load, in Python you use pip,
Yes.
right? And you have to include a requirements.txt file,
Yes.
for example, and then that tells Python
Which
dependencies it needs to download. So in Go, you have a Go modules file, but that did not exist yet when I first created this in 2019. So I'm going to say Go mod init, and I'm going to call it normally you won't have to do this, but we have to this time because I'm upgrading an older version. So we have to give it the name of the package. So we'll call it GopherCon 2019. So now that created this mod file, which all that is it says it's the name of the package, like the root package, and then what version of Go. So we haven't actually installed anything yet. So we're going to need to get we need to say go get, and then we'll say tinygo.org x drivers. So this is how we get the drive. Well, we don't even need that yet, actually. We don't even need that yet. So right now we have this Go modules file, but we have no dependencies because all we're using is the built-in packages in that program. So now if we go to the instructions here, that we should be able to just copy and paste this, right? So what this is, or we can just type it in, which is we say tinygo. So if I just type tinygo, it'll give me a list of the different subcommands, similar to Git or many other programs. So it's got these subcommands, right? So if I say tinygo flash, then it'll flash the board. And, all right, so tinygo flash, and then we have to say target. And which target is it? The target is the Arduino Nano 33, which is the board that we're trying to flash here. And then which program should we flash on it? Well, we want to put step 0. So now, once again, just to kind of reiterate, so we have tinygo flash to flash the board, telling it the target, which is which kind of board it is. That way, the tinygo compiler knows which type of processor it's trying to use, which type of references for that machine package, so it knows the machine.led and what that refers to, and then which program it is to flash. So now when I hit return, it'll compile the program, and then using the BASA flashing tool, it flashes it onto the board. So if we take a look here at it under the microscope, we can see that in fact the blinking LED is blinking, and so now it's actually working correctly. So that solves that problem we were having the other day where we couldn't flash the board because that was an older board that had it was one of a bad batch of boards that were the very first ones manufactured. A couple of them were defective, and I just happened to have a few of those around, and it got mixed in accidentally with... So now, let's go take a look here. So that was step 0, right? So now, we want to do step 1. Step 1, which is to use the blue LED, which if we go and we take a look here, the different items we have, here's the blue LED, and we could take a closer look. So these are sensors that I was given by Seed Studio, awesome company out of China. And so they use a kind of connector that's called a Grove connector. And the Grove connector makes it very easy to connect different parts, peripherals, components, without having to solder anything. So we just need to use one of these cables. these Grove cables. So these particular cables are very cool because on one side they have that Grove connector, so we can plug that in, and it makes a little satisfying click. See if I can get the focus really focused in. And then on the other side, it has these DuPont type connectors, which are easy to plug into a breadboard, which it just so happens that we also have the breadboard. We're not going to use this display yet, right? So what we want to do is we need to plug in the connector for the Arduino. Let's see if I can get the cable to reach here. Yeah. Right, so we want to plug in the power, the ground, and then we'll plug in the pins for the LED, right? So if we take a look and we can see closely, first of all, the power, and if we go take a look at the illustration here on the website, and we have that picture. So the power is the second pin from the end where the USB is plugged into, right? So I'm going to go and I'm going to plug the power into that pin. Let's go back to micro. So I'm going to plug the power into that pin. And then I'm going to plug that into the red channel on the breadboard, the one that's got the little plus. Then I'm going to plug in the black. I had a black cable here a minute ago. Where'd it go? Did I drop my cable? Impossible. That was so quick. It didn't survive. Luckily, I have lots more cables somewhere. Oh, here it is. We could actually focus a little better. All right, so now we're going to plug in the ground. So the ground on the Arduino board, any of these spots, any of these pins that have the little white marking on the tab, turn the light on. Is that better? No. Oh, close up, yes. So any of these with the little white marking on the tab is ground. So I'm going to plug that in. And then I'm going to plug that into the ground on the other side. Okay, so now we got the ground and we got the power coming off of. So here, why don't you plug in the next ones here? So you switch with me, going to the other side here. All right, and so now on this Grove board, I don't know if you've used Grove kits before.
No.
So one side is just a connector that just clicks on.
Yes.
And then the other one, it turns out that it's labeled, but you don't barely even need to know that because it's red is power,
Yes.
black is ground, and then
Signal and
one of these other ones is signal, and then the other one is not connected. But if we go to our instructions here, then let's see.
yeah, in here there is no mention.
Well, it's on there, but it's really small.
Hmm.
But you can see here that it's the yellow that goes to, so the black goes to the ground.
So I will use the same as here.
Exactly.
Let's do it here. And the positive, I can use the red line.
That's right.
That's one. And the signal, where do we
Is
pick
the
it
yellow, and that one wants to go into pin 12.
Pin 12. Let's
So
have a
pin
look.
12
It's like that.
is, if we look on the,
It's
it's the
digital one. Yeah.
on the
It's
first pin on the left,
left upper side. I guess
on the
it's
upper
this
side.
one. Whoa. And
Exactly. Okay.
see, yes. So we can tune it probably using this trimmer because it's a very low signal right now.
Yeah.
But it's blinking.
So let's go take a look at the code.
No, it just stays on. I don't see.
Well, we haven't run the code yet.
I see it's doing something, but I don't know if you can see it on the screen.
I don't think.
It's a very random behavior. Ah, it's my body.
Oh yes, you're
Yeah.
acting as a ground.
Exactly.
So let's go look at step 1, the code here. So step 1 is almost exactly the same as step 0. We have the same package main.
Let me guess. Here the difference is that we are pointing to a digital pin output, D12.
Exactly. That was D12, and you remember we plugged in that pin
Easy.
into
Yeah.
the output for D12. And otherwise, it's exactly the same program. Configures it as an output, sets it, turns it off by turning it low, sleeps for half of a second, 500 milliseconds,
Turn it up.
turns it on, and then does the same thing. So now if we go to the my terminal, and now if instead of step 0 I do step 1, then
We flash.
we should be able to flash it.
I'm not touching it, so not to interfere with the.
And so now it compiles, it's flashed, and then
here we have it.
and now it's blinking.
Absolutely.
Okay,
Fantastic.
so we made it through step 0 and step 1.
That's great.
Okay, so that was some progress.
2% improvement.
Yes, yes. All right, so now next time you're going to have to bring your own computer, and then we'll plug in that, and then we'll also we'll go through the rest of the parts in the kit here because there's quite a few of them. So I think you have your bag.
Yeah.
The
Yes, the
plastic
main bag is
Yeah,
here.
don't lose that because you're going to need that.
Yeah, let's put some order in here again.
And so I'll give you back your board. So as you can see, this actually works this time, not like last time.
Yeah. Fantastic.
This kit is much better. I just had to dig through my piles of boxes to try to find, the original working set of. I've given a lot of these away, mostly thanks to Arduino, who has been a tremendous sponsor and group of friends, and they do. I mean, you can't really beat Arduino for.
Absolutely. I'm a fan, absolute fan with Arduino. I think all this kind of tinkering at home, it's just thanks to Arduino community. It's a fantastic support, and I started playing with those things, and I wasn't thinking I could do electronics with that approach. It's just plug and play. It's fantastic.
Cool. Well, okay,
Okay.
you got your homework, so next week we'll go on to the next step.
Thank you very much. It has been a pleasure.
All right. Thanks for stopping by.
Thank you.
All
Bye,
right.
everybody.
See you next week.
I leave you.
No, you got to take that with.
I'll try. Okay.
No, you really got to take it.
Okay.
You actually have to do your homework. This is
I'll-
not
I'll
just a.
do. I'll
This
do
is this is reality, man. You actually have to do it. Okay. That was really fun. So I hope you enjoyed that as well. Yeah, we're going to go through each week. We'll go through a different step. And we will hopefully, by the end, we will all know how to program devices with TinyGo. Well, at least on the, starting level. So, so I was showing you earlier the, where did it go? So we've been doing a lot of work to get ready for the next TinyGo release. And probably one of the biggest things that we've been doing, which we're really, really excited about, is our new website. So it's not done. There's a bit more. But this is the landing page, and we've revamped the structure of the website considerably. I mean, it looks nice, and a lot of that is because of using the Doxy Hugo theme. So Doxy is actually a project from Google, but not an actual official Google project. So Doxy is a theme that lets you create documentation sites with some particular characteristics. In our particular case, we organized it in obviously the getting started section is really key to helping you get started with whatever operating system you might be having to use. And the documentation itself has been structured now based on the documentation format that was really pioneered by Divio. So Divio created this, it was actually one particular person, and I forgot her name right now. It's not David Lang. It's, all right, I think we better look it up. Just because he has gotten the, the biggest fame for it, but is not actually the creator. Oh, well, where is it? It was a person that created this at a really awesome talk at PyCon Australia. Well, I can't find it right now. But anyway, so this documentation format separates it into 4 sections. You've got tutorials, which are step-by-step leading you to teach you how to do the things. You've got guides, which are also somewhat step-by-step, but as opposed to a tutorial where it explains all of the whys and what you're doing, the guides are just telling you how to accomplish a particular task, listing out the steps. Your concepts, where we are explaining important things like the compiler internals of how TinyGo happens to work, and all of the conceptual ideas that you need to understand to come to a deep knowledge. And then the reference, which are things like the actual API documentation for each of the different platforms. And so by separating the documentation into these sections, we are hoping that it'll be a lot easier for people to navigate the information, and also to have people to contribute more, because we discovered that the documentation was just getting huge and a little unwieldy, and the original website theme wasn't really keeping up with all of the work that we were doing. So kudos for all the people who've been helping with the documentation rewrite. So in addition to that, we've had lots of exciting work going on, in particular WebAssembly. There's a whole group of people at Fastly who are doing some really, really interesting things, and a bunch of that work has just landed in TinyGo, thanks to several different contributors. And so WASI support, which is the WebAssembly application API that's used not just for browsers, but also for non-browser implementations like the Envoy proxy, where you can create proxies using WebAssembly and TinyGo. So we've had a whole bunch of interesting contributions that have come through, and if we go and we just take a look and we see we're really overdue for a release now. But we were holding back because there was a couple of bugs that were discovered as a part of this really intensive testing effort. So thank you so much to the community for, helping find some of these bugs and also helping solve some. So we're 140 commits ahead of the release, and there's just tons and tons of stuff in here. Not just the WebAssembly fixes and updates, but we've also got some new platforms. We've got some performance improvements, and just this is going to be an amazing release. So one thing I thought I would do is we have the TinyGo's drivers repository. So the TinyGo drivers repository is where all of the sensors and displays and other types of peripherals that we use to communicate with the outside world or to get information from the outside world. So we currently have support for, I think, 57 in the dev branch, 29 commits ahead of the release branch. So yeah, we definitely need that release. So 58, wow. The numbers are growing. So we have a couple of pull requests that actually just came in. One of them in particular, I think is just really, really cool. It is the new tone package. So Ika, project founder and major contributor to TinyGo, has been working on the pulse width modulation capabilities of TinyGo. So you might recall that we talked about this a couple of weeks ago, where pulse width modulation is a way for us to, without having an analog signal, for us to sort of simulate an analog signal by turning on and off a digital signal quickly enough that we could, for example, only have it on half of the time, what's called a 50% duty cycle. Then it would only provide 50% of the overall strength of that signal, and so something like a motor would only be at half speed, right? So one of the ways we can control things with pulse width modulation is we can control speakers. And that is, in fact, a very common way of making speakers produce audio. So Ika has been working on a new driver. Excuse me. So let me git pull rebase origin dev on the drivers repo so we can pull in all of the latest goodness. And let's go take a look at this new tone driver. It's in here somewhere. Okay, so the tone driver, actually, let's go take a look at how it's used, because that is a little easier than looking at the implementation. So in here somewhere, we have this tone example. So the tone example, package main like we normally see, the machine package, the time package, and then the tone package, which is this new driver. So this particular example is set up to use the Adafruit Circuit Playground Bluefruit, which it just so happens is the board that we have attached to GopherBot. I think you can imagine where this is going. Yeah, let's. So these are the two pins The first one is to configure the pulse width modulation capabilities of the Circuit Playground Bluefruit board, and then pin machine D12. Remember D12 we were just using in our other example? Well, in this case, D12 is going to be the pin that is connected to the speaker. So if we look at the main program, so the first thing we do is we create a tone.new, which creates a new tone driver, and we're going to pass it first the pulse width modulation bus to use, and then we're going to pass it the pin to use. This is so that you can use a single pulse width modulation circuit to control more than one pin. Like, oh, thank you. If you have, for example, multiple motors, you can control multiple motors at the same time with a single pulse width modulation circuit. All right. So we created a new one, and if there's an error, then we'll return. Otherwise, forever, first we will, I guess this is Dutch for, you have do, re, mi, or C, D, E in the American music spoken notational system. So I guess in Dutch, this would be so, T, no, T. Anyway, yeah. So we're going to print ni, and then the speaker will set the note equal to the tone of B5. So B in the fifth octave, and we'll set that note, and then we'll sleep for 2 seconds. So because we already turned it on, it will just stay on how it was for 2 seconds, playing this tone. Then we'll print na. We'll change the speaker's note by saying speaker.setNote to tone.A5, which is A, slightly lower in the same octave, fifth octave, and then we'll sleep again for half a second. So it basically is going to make this alarm siren go off, and it is kind of loud. So let's go over to the dev, and let's make sure that we have the right TinyGo version. Yes. Okay. So now if we say TinyGo flash, and we set our target equal to the circuit play Bluefruit, which is the board again that is built into GopherBot right now. And our examples that we're going to use the tone example. So if I plug in my cable into GopherBot, then we're going to reprogram GopherBot to make a lot of noise. Okay, we're plugged in. So now if we flash the program, and there it is. Yeah, you definitely can hear that. We need to program a way of turning it off, probably. All right, so that works really well. Good job, Ica. So yeah, that's just one of the drivers that has been added to the drivers package for this next release. And there's actually a couple of pull requests that are outstanding that I wanted to try to merge in. So one of them is this driver for the TM 1637 7-segment LED display. So let's take a look at this display because it's actually really cool. Extremely old school. So yeah, you can see here This is the Adafruit version, and it's a classic type of 1970s, early 80s war games, countdown of some type of, detonator or whatever. The end of the world is going to be counted down on a 7-digit LED clock, apparently. But in all seriousness, one of the main advantages is how little power that this display uses and how readable it is, right? So Alan has done some really cool projects with TinyGo. One of the projects that he did last year that I thought was really awesome was a customized TinyGo powered Millennium Falcon, where the model was controlling its lights thanks to a TinyGo program he'd written. So this pull request has been sitting here since July. And I felt really, really bad. And now there's a merge conflict. I can't ask Alan to do anything about that. I got to just merge this in. So let's go deal with it. So the first thing I'm going to do is we'll check out we'll create a branch. We say git checkout -b for creating a branch. The Alan Krantis TM1637 branch, and it'll be based off of the current dev branch. So then the next step, patch. I don't want to patch. Hold on. Use the command line. Command line instructions. That's not what I want to do at all, actually. Wow, that is a really strange set of instructions. What I actually want to do is I want to pull in, this repository has been deleted. Oh, wow. I think it's just been too long. Well, I guess I'll try to follow this. I've never done this, merging the patch via curl. Let's see what happens. Okay, that actually worked. So now it's got the makefile conflict. This is this TM1637 driver that we just added. That's the sample that he added. And so let's go to the makefile. And so the makefile here, we see it's a classic case of where there's two different changes in the same space. And what we actually want to do is accept both changes. And we also are going to want to add the sum total. That way we're getting the correct totals in between each one. And again, going back to this was an Arduino Nano 33 board that is compiling that example. All right, so let's make sure that that actually works by building this example. And we could do that just on the command line. So yes, it does build. All right, so now in order to resolve the conflict, now we just do a git am continue. And that will continue the rebase operation, or patch, whatever it is here. Okay, so we still have, because I didn't actually, we have to git add makefile. And then we can continue. And so now, if we look at our log, we can see updates the makefile. All right. And so git status, we have all the files. So now we're done. We're middle of the AM session. And we basically have now resolved the merge conflicts. And we are ready to go. So untracked files is this other example I was working on. So now we've actually successfully resolved the merge conflict, right? So now if I go and I git checkout dev and I git rebase from the Alan Krantis TM1637, and I can take a look and I see those commits are now in, even though I actually meant to squash them together. So let's go do that. So if I say git rebase-i for interactive, and we say head tilde 4 for the most recent 4. So now I'm going to pick the first commit. Actually, I'm going to reword the first commit because I would like to change the, and then I'm going to fix up the remaining 4 commits. So this way I'm grabbing these 4 commits and I'm putting them all together into a single commit. And we will say TM1637 add support for TM1637 driver. Now, just before I do this, I just want to, because there was something that was kind of bugging me, and that was there was a pull request already merged in somewhere of another similar display. And just before I actually merge this in, I just want to make sure that I'm not accidentally, no, that was a 4x4 keypad. I seem to remember the max. Okay, that's a different one. All right, we're still okay. So add support for the 7-segment LED. Okay, so we save that, and now if we take a look, we see now it's all in a single commit. And let's just make smoke test just to make sure before we go and we push this to the dev branch that it actually passes all the tests. Yeah, it looks like he deleted the repository, must not be doing any stuff with TinyGo at the moment, or didn't need an extra copy. He had already done the things he was going to do and didn't want to end up with a fork that was way out of date with the master or main or release. So let's just let it do its thing. It's almost there. There's quite a few drivers in here. And actually we need to update the list because now there's one more. Because I don't think he added to that list in the README. No. Okay. Did not. So, yeah, we need to add it to the list. That way it shows up in there appropriately. So, I'll probably not do that right now. I'll do that before the release. Only because that way if we have any other pull requests that we want to merge with any other drivers, we don't end up with yet another merge conflict that is only because of the text in the text file, right? That just makes it a little easier for us to try to get some of these new changes merged in, because Did I mention we're getting ready for our TinyGo release? Yeah, it's going to be awesome. It's actually going to be one of the best releases yet. The WebAssembly capabilities, the improvements to the garbage collection, the speed up of a whole bunch of different processing, the compiler itself. So, all right, so it passes all the tests. Everything is in there. So if we git push origin dev, then we made it. And so I'm going to say I resolved the merge conflict and squashed the commits. Actually, we should say something first like, sorry it was so long to review this PR or this contribution. Somehow it was overlooked. I mean, it really was. I saw this, a couple days ago, and I'm like, wait a minute. Why didn't this get merged in? And then thank you very much. I resolved the conflict, the merge conflict, and squashed the commits. It has now been merged into dev. Thank you very much, and we close it because it was, in fact, actually merged. All right. Yes, we did it. Let's go take a look and see if the build is built. Uh-oh, something failed. Oh, okay. We have to add this to the unit tests. That's right. So in the TinyGo drivers repo, I probably should have just run make test. So in addition to the TinyGo smoke tests, we also have some traditional style Go tests that use the, in most cases, it will use a mock or a stub of the device that is trying to be tested. In this case, there isn't one because that particular driver uses just, what does it use? GPIO. So we needed to add that to the tests. And I think if I just say make unit test, then that should verify. And then I'll have to, so yeah, now it passes. So, whoops, my bad. So now I'm going to have to squash that. I hate that. So git add makefile, git commit, and we'll say the, what was it? The TM 1637. And then correct, exclude actually, from Go unit tests. All right, so now we want to say git rebase dash, I don't want to rebase it. I feel like but I also don't want an extra commit. Well, I have to rebase it because otherwise I'm going to make a mess. So git rebase dash I head tilde 2. And so we'll just pick the first and we will fix up the second, and then git push origin dev force, because now I've squashed a commit. And okay, that is a little messy. That's a little messier than I planned, but it's okay. I probably should have run both of the tests first, and no, probably, actually, I should have. I fixed the commits, and now it's not messy anymore in the commit log. However, if anybody happened to pull the dev branch in that in-between period, then, well, naturally they're kind of, wondering what just happened. But that's okay. What can we do? So let's see if we're running the tests. Let's go take a look at our Circle CI build. Actually, I could have just looked at it here. And so it is building. So while that's doing that, let's go take a look at any of the other pull requests that maybe are outstanding, that are looking interesting. So one of them that I was checking out earlier today was this contribution from Ken Bell, which is adding the INA 260. So it's a current measuring device. It's actually a very interesting device for measuring DC current only, not AC current. But this particular voltage sensor can support up to 36 volts. So if you're using it for industrial equipment or automotive equipment, which is at least 12 volts. Automotive is 12 generally, 12 or 24 sometimes. Industrial equipment is 24 or 36 even. So you want to be able to measure that voltage, and you want to do so in a way that is safe for the devices in question. Well, this is a pretty good device because you can measure it from the high side or the low side, meaning if we are stepping down our voltage because we have, a 12-volt battery and we only need 3.3 volts for our digital electronics, or vice versa, we're using a power regulator to step up to 12 or 24 volts for some lighting or something, or some motor, then for the control voltage, probably in that case. So this particular pull request does a little bit more, though, than just adding the voltage sensor. He also has added a something I think that ended up getting put into a separate pull request as well. I think this is it. 16-bit register mock device. And I believe this is 16-bit register mock device. Yes. Okay. So we should probably merge this pull request first. So what this does is this is a, I was mentioning the regular Go unit tests that use the standard Go test command, and that some of the drivers in the drivers repo have these tests written because they're able to do so by way of this mock device. I think it was originally created by Roger Peppa, and then modified by a couple of us, and that's what is currently being used in the drivers repo for testing. So this particular device is a little bit unusual in that it has 16-bit registers. Normally, I2C devices handle bytes at a time, but this particular device, it has, instead of just 1 byte, all the registers are 2 bytes. So the reason why that matters is that if we want to easily mock and test this, you can take a look at that here with this device 8 test. No, let's see. Where's the test for the... Oh, we have to go look at the actual pull request for the INA 260. So if we go and look at the actual pull request, we can go and we can take a look at the tests in here. Here we go. So the tests that were added, it's using Quick Test, which is a Go package for test assertions. And then it's using the tester package, which is a package as a wrapper that was added to the TinyGo drivers repo to make it a little easier to handle the mocks and stubs that we have predefined for you. So you can see that this is a 16-bit, in other words, 2-byte register device. And so in order to easily test the values, because they're 32-bit, not just 16-bit even, it's 2 registers, I imagine. So 4 bytes. Wow. And so the default registers, which is how we do our testing, is a map that we define, and that contains the register definitions and then whether the default values or the values that we're going to use for testing. So you can see here that the config register has got 16 bits or worth of data. So in order to easily test this, and here's an example of 8-bit registers, right, versus the 16-bit registers. So it's a little easier to write these tests, and that's where he actually created this separate package to do the testing and stubbing. So if we take a look and see whether some of the comments that were made here. So Ika thought the contiguous design was better. Splitting the data store and the mock interface. Yeah, kind of did that. So the 244 is 2 mock implementations with a common interface. And that's what we were just looking at a minute ago. That we have in this pull request, which is separate, defining both the 8-bit and the 16-bit test structures. And let's see if we can find the... So I guess this is actually adding a new package, this tester package, because I don't remember that being in there before. If we go and we take a look at the drivers repo, there is a tester package, but not those particular parts of it, right? Well, now that I look at this a little more closely, let's see here. So the 16-bit's got the same interface. It tells you how to use the mock. Generally, people are going to use the I2C device 8, probably. I just wonder if maybe, this pull request has been around for a while and it desperately needs to either be merged or to have some feedback so that some changes can be made to it. And generally, I have found if you're not confident, don't merge. So, but I feel like it should be about there. So, seems like all feedback has been addressed. So all feedback so far has been addressed. Ika, what do you think? Of the changes? All right, and we'll see if maybe if Ika likes it. It seems like it's okay. There's no way to get around the fact that you're going to have to do something at least a little different. Let's see if there's any other pull requests that we can maybe merge in. I think this is also, this is another pull request from Ken Bell that includes the same mock. So yeah, he's got two drivers that could be added if we can figure out how to get the changes to the mocking interface merged in. That seems like a definite winner. Okay. Yeah, well, I'm going to just wait and see what happens. If Ika likes it, then we will take it. If he wants some additional changes, then we can go ahead and, I guess, make some additional changes. All right. So speaking of changes in the driver's repo, so before we were taking a look at the Arduino Nano 33, which is that this is kind of the, I guess, the week of the Nano 33 board. So this particular board, as I've mentioned in the past, has got two microcontrollers. It's got the AT-SAM D21, which is an ARM 32-bit microcontroller based on an ARM Cortex M0. And then it also has a Wi-Fi coprocessor, which is made by uBlocks, but is based on the ExpressIF ESP32, which is a separate microcontroller used generally for nothing except Wi-Fi and, in some cases, Bluetooth. So this particular board has got its own firmware, and that firmware that is generally run is something which is created by Arduino, and it uses two parts to it. The firmware itself is known as the Arduino Nina W102 firmware, or so this is actually what lets you connect to this chip using the SPI interface, the serial peripheral interface, and communicate with it from the board directly. So if we were able to look at the layout for this board, actually we can look at the schematic. Arduino Nano 33 IoT schematic. So the schematic is the drawing that shows exactly all of the different parts. No, that's, I just want to find the, maybe this is it. Yeah, here we go. It's a very small version of the schematic. Oh, I bet I can find it on the Arduino site. Under the technical docs. Let's see. Here's the schematic. All right. So here we have two different, a little hard to see. All right. So here's the schematic for the board. So we can see here that there's a couple of different chips, right? We've got the main processor, and then that is connected via two different sets of wiring to the ESP32 Wi-Fi chip. One of them is through a UART connection, a serial connection, and the other one is through a SPI connection, which is the much faster serial peripheral interface. The reason for this is that you really need to be communicating as fast as possible with your Wi-Fi chip if you want it to be able to keep up. So when we first introduced support for the Arduino Nano 33, the way that we did it was using the firmware that is provided by ExpressIF, the so-called ESP-AT firmware. But then we discovered two things. One is that the Arduino Nano firmware is already installed on all of the boards that are sold by both Arduino and Adafruit that have this particular Wi-Fi chip on board. So the Metro M4, which is from Adafruit, the Feather boards that have the Wi-Fi built in, also from Adafruit. There's a bunch of boards that have this already built in. And that firmware is already preloaded with the Nano firmware. So we switched over to use in the TinyGo drivers repo. We switched over to using a newer driver called the Wi-Fi Nano driver. And the Wi-Fi Nano driver is what allows all of the SPI interface using the different API, which is provided by the Arduino firmware. Okay? So far so good, except turns out that this firmware has gotten updated. And then it also turns out that the firmware that we have support for is not working. Let's see here. I want to say Nina? No. I know it's one of the main open ones here. Yeah, there we go. Excuse me. So this bug was reported by Nerzal, and so they were looking at the code to try to fix these particular problems. The nature of the problem is that the packet size, the actual packet format was changed between the original version and this newer version. And so they were working on making these changes in this pull request, and then ended up closing it because it turns out that B. Gould had already been working on a Wi-Fi Nano refactor that had never gotten merged in. So what I would like to do is I would like to try to take the changes that were made, which unfortunately these changes are not like complete or finished or ready to be merged. B. Gould was working on it and then got busy doing some other things. So they're also quite old. You can see that it's from June of last year, and there have been a lot of changes since then. You can see certainly, for example, that there's a bunch of merge conflicts. Essentially, all the examples have a merge conflict, and the core of the Wi-Fi Nano itself. So this is not going to be easy to get this sorted out. However, we need to get it sorted out because all of the boards that are being shipped with this Nano firmware are in fact no longer compatible with the version of the TinyGo firmware or driver that we're shipping. And I think that probably the 1.30 is the last version that actually works. We can figure that out. No, of course we can't figure it out easily because if we didn't version. So here in the TinyGo drivers repo, in order to make it easier for you to build the firmware, so this firmware is actually, here we go. So building the Nano firmware and then flashing it onto your board requires installation of the full Espressif 32-bit toolchain. And that was a little too complicated for many people. So what we did was we created a Docker file. And so if you want to update this, you can just build the Docker image, and then you can run it, and it will generate the firmware files and put them into the build directory, and then you can flash them onto the board. So this is still working, and I did this actually, was it here? No, it's different firmware. Let's see. I did flash the latest Wi-Fi Nano firmware onto one of my Nano 33s. So if we go and we look in the, I think it's under Wi-Fi Nano. Yes. And if we say Docker, yeah, I think that's it. All right, so that builds the Docker container for the Wi-Fi Nano. And now if we run it, then, let's see here. So Docker run, using the -v for volume, which is what lets us mount the current directory's build directory into a directory that the container can see called source build. And it's going to run the container called Wi-Fi Nano. And so this is going to do the compilation because it already has the whole tool chain installed. Aren't you glad you don't have to figure out how this works? I think I wrote this Docker file, and it took a while to get it done. I was willing to put in a lot of work to avoid having to do future work. But I was not entirely successful because, yes, I can build the firmware, and I can even flash the firmware, but then I cannot execute the firmware because we need to update that driver. So, but first things first. So we're going to finish building the firmware, which, as you can see, it's got a lot of dependencies. It does a lot of work. And then once we've built the firmware, then we have to flash it. And the way we flash it is we use a tool called ESP tool. And ESP tool is a Python flashing tool that is used to flash both the ESP32 as well as the ESP32 or 8266. Okay, so now we've built the binary, right? And so now, in order to actually flash it, what we have to do is keep in mind the following. All right, this is a little tricky, but come with me. So I showed you the schematic for this Wi-Fi chip. And I showed you how it was connected to the main microcontroller chip on the board. So you might be wondering about now, how are you supposed to update the firmware on this chip? How do you connect your computer directly to this chip? Well, the answer is you don't. There is no way to connect your computer directly to this chip. None of those pins are exposed directly on the board itself. Well, that's not strictly true. There are some, I believe, JTAG connectors on the backside of the board, but that's not a practical solution for most people. So it turns out that there is another way, that what you can do is you can, by using the Arduino sketch, so let's run Arduino here. So the Arduino IDE has a sketch. Sketches are programs in the Arduino world. And so now if we go to our examples, and I've already installed the board package for the Nano 33 IoT, and I've also already installed the Wi-Fi Nano library. So I see under Wi-Fi Nina, I see some tools, and one of them is called the Serial Nina Pass-Through. So what this does is it plugs in the serial port, the serial data that comes in from the USB, and then by using the Arduino program called Serial Nina Pass-Through, it is able to literally just pass those bits along. Where's the part of the code that's, it's kind of messy because it has to support all these different variations, but it reads from the serial port and then writes to the Nina's serial port, thereby passing the data along, hence why it's called the Serial Nina Pass-Through. So when we put this sketch on our Arduino, which we'll do right now by plugging it in, and then we can go to our tools. It recognizes the board that it's plugged in. So we'll go ahead and compile the sketch and upload it. Now it's done. Okay, so it's not doing anything because now it's sitting there waiting for something to happen. And that something to happen is for us to take step 2 here now, right? So we flashed the firmware on there with this Nina pass-through. So now we can take and upload the actual Nina firmware by sending it to the Arduino, and it will just pass it through directly to the Wi-Fi chip. It's a good thing you don't have to do this all the time. So it is ESP tool on this big, long, ugly command line. And I believe, yes. So now if we run this, it was able to connect, erase the flash off of the ESP32 that was on board, and now it is actually writing that data by way of the pass-through to the coprocessor. So there's no other way to do this that I know of other than if you have a JTAG connector and you have, pogo pin interface or something where you can plug directly to the pins on the chip itself. I don't have any easy way to do that wiring. So I know you maybe want, this is the easy way? Yes, this is the easier way because at least it's a way you can do. So now we're updating the firmware, and once we've got that firmware updated, then of course we can test this out, and it won't work because there is in fact a difference between what this firmware expects and what the current Wi-Fi Nina driver that's part of the TinyGo drivers package. So we need to update that, or else people are not going to be able to run the latest firmware. So we're probably going to need to do something where it supports both versions of firmware, because a lot of people are going to have the original version of firmware and no way to conveniently update it. So we have to figure that out as well. All right, so now we've updated the firmware, we put it on there, and so now if we go to the TinyGo, if we look at the samples, right, the examples, and we look at one of the Wi-Fi Nina examples, which is in here somewhere. Here we go. So we can just pick a relatively simple one, like, for example, I don't know, MQTT client. That's not simple. Well, really, no networking is simple. But what is the NTP client? Yeah, that's, I haven't tested that myself. That uses the UDP interface. Well, let's go back to the MQTT client. So what this does is, you may have seen this demo in a couple of my talks and some of my demos. So what this does is it is going to connect to the Wi-Fi, and then it's going to connect to an MQTT server. Specifically, it's going to connect to the Mosquito server, and then it's going to, once it connects to that server, it's going to publish an MQTT message basically every millisecond. That's kind of quick. I would say that is way too short. That's definitely a bug. At most, we should do this once, 10 times a second, let's just say. But of course, it's not going to even get that far because it's not going to be able to connect to the access point, because we already know from the bug report, oh, thank you, gracias. From this bug report here, we already know that the Wi-Fi Nano was not able to connect, and it's firmware greater than or equal to 124. And if you remember, when we took a look at our releases here, or their releases, I should say, I don't even know where 124 came from, because I don't even see that listed under the releases. There was a 110 and then a 130. So I would assume that essentially no version that anybody can easily get. And keep in mind that this release took place in 2020. So almost for sure, this has been the version that's been shipped out on all these boards for quite a while. Right? So we're going to have to do something about that. But first things first, so let's see here. I'm going to need to enter in the SSID info in order to, and I forgot it myself. What is that? Hackspace. And then the password, which I can't show you. I have to scroll off the screen. And then, I guess, change to this view while I type it in. I know I've forgotten something. I can't even remember it myself. How funny. I think that was it. Let's see. It's probably written down somewhere on a scrap of paper. Yeah, that's what I thought. Okay. So, I'm going to have to scroll off the screen so I can't show you what it actually is. High security, high security. All right, so now when I go to the driver's repo, I should be able to TinyGo flash, and then my target is the Arduino Nano 33, and the examples are the Wi-Fi Nina, and it's the MQTT client. So we should be able to flash the board. And yes, it flashed. And now if I go over to my, I can see that my terminal, which is my serial connection, is so far not able to connect, right? It's just saying connection status idle because it's still trying to reconnect, but it's not able to do so because of this error that was mentioned in this bug here. And tested with 2 different firmwares. But then also took a look at this branch from B. Gould with the Wi-Fi Nina refactors, and so I guess the question is, did this branch work? So let's ask that question. Did you ever get a chance to test the B. Gould branch to see if it corrected the same issues you were having? I am willing to work on this to help if it actually corrects the core issue. Thanks. All right. Make sure Nursal knows that. Yeah. All right. So we will see if they are. I'm absolutely willing to work on it. I actually tried to do a little experimenting with this before, and it turned out that these merge conflicts were quite major, like really big. Like I couldn't figure out what, if anything, to do about it. Like nothing was happening. It tries to connect, and then it never receives it actually doesn't get any message back because it doesn't send a complete packet of information to the Wi-Fi processor to cause it to try to even make the connection. So it's going to be a bit of work to fix this. I started taking a little look at what was going to be involved. Let's get reset hard. So it was in this branch, what's it called? Wi-Fi Nina refactor? Yeah. So I tried to actually do something about this. Let's try again, see if anything happens. I'll show you what I'm up against. So if we get branch -D to delete the... All right, so yeah, I probably deleted it. All right, so first we'll check out that branch in our driver's repo. So we say git checkout B for branch, and we'll create this new refactor off of the dev branch. Then we'll pull in the B. Gould changes. The difference being instead of git pull, we'll do git pull -- rebase. That way we don't end up with a merge commit. And yes, there are many merge conflicts. So the two that really matter really are the ones in Wi-Fi Nina.go and TCP.go. Now, interestingly, the TCP.go is the one that it appears was not able to be resolved automatically. What is, in fact, the problem there? Let's go take a look. So, TCP.go, there's a couple of problems. One of them here is, so now keep in mind, right, what are we looking at? The current change is what is already on my disk, and the incoming change is the new change that's coming in. So you can see here that, in fact, it's just adding some code that was not there in the previous, so we can say accept incoming change. Okay, so then we look at the current change. It's got this DRV proto, which we already defined above here, right? We already assigned that. So we want the incoming change. And now is where it starts to get a little messy. The current change has got, it's checking to see if these errors, I guess it's very similar to the incoming change, just adds a little more data to the error message. So let's accept incoming change. And then this adds this return len b at the end of this, which it looks like is never going to be called because in this if above here, both the if and then the else both return len b nil. So probably that's not right, but I would guess that line of code will never be called. And then, all right, that looks like that resolved all the conflicts in tcp.go. All right, so far so good. So now let's go take a look at the other ones that need to be resolved. We have, let's see, 2 examples. It is the UDP station and the NTP client. So let's go see if that's a small problem or a big one. Need to clean up a few directories here. That's the actual code. What we want is the examples. And the 2 that have problems are the NTP client and what problems does that have? Let's see. So the current change and the incoming change. So it looks to me like, I will guess that the new format for Wi-Fi Nina matches the original. But if we don't, let's go take a look and see. I don't know if I'm going to be able to do this quite so easily. So if we go to drivers, dev, maybe it was a little ambitious to think I was going to get this to work and communicate with a Wi-Fi. And we look at the, actually we should be looking at the actual driver definition, which is here. And so the, when we create on Wi-Fi Nina, we do it by saying new. Is there a new SPI? Because that's what it thinks it's called. It looks like there is no new SPI because, in fact, it's now just called new, and that's returning a device. And so this is, we're checking in the client, or one of the example applications, actually. And so that would mean that it's probably actually called new SPI and not this. So we probably want to accept the current change because that was revised subsequently. Then looking at we can accept the incoming change because that's just doing a little more error checking. And I think that's it. Yes. All right. So now we'll go to the UDP station. Probably has the exact same deal. I will accept the incoming change since we probably have that dependency. I will accept the current change like we did on the previous example. And then, I don't know why this is doing this. It's basically writing, 25 times. All right, so I'll accept the incoming change. And that's it. So now, potentially, we have made the necessary fixes to, so if we add examples Wi-Fi Nina, and then also the Wi-Fi Nina, then we should be able to continue our rebase. So we get rebase, continue, and now we hit the real merge conflicts. No, only one, and that's in Wi-Fi Nina.go. So Wi-Fi Nina.go, down here. And yeah, there's a bunch of problems here. Let's see. I will guess we will accept the incoming change. And then over here, yeah, I'm just going to accept the incoming changes. It seems like that should be correct. I guess we'll find out. Yes. Usually, the incoming change, meaning the new changes, you can superimpose them on the existing ones, but not always. I guess we'll find out. Okay. And I think that was the only one. So yeah, so we add Wi-Fi Nina, get rebase continue. Okay, now we hit a massive number of merge conflicts. Yeah, there's no way I'm going to be able to finish this in the amount of time that we have remaining for today. So I'm going to have to keep working on this rebase operation all night long. Well, no, I don't know about that. But I definitely have to do something because I need Wi-Fi. You need Wi-Fi. We all need Wi-Fi. And this is the easiest way to do it, probably. Hopefully. I guess we'll find out. So, what did we get done today? Well, we had a fun time getting to have some learning to TinyGo with my programming chum Lorenzo. We merged a pull request that was almost a year old for a driver. We took a look at a couple of other driver pull requests, some of them involving enhanced testing, and that should definitely be helpful. We took a look at some of the changes that we're going to need to make in order to resolve an incompatibility with the Wi-Fi, and we were able to flash our Arduino Nano 33 IoT board with the latest firmware. So that was pretty useful. I didn't even have time to do some of the other stuff I wanted to do today, which actually was, I brought with me my Jetson Nano kit from last week, or 2 weeks ago. Actually, this has been going on for weeks already. So I managed to get it into the case, but the thing was, I discovered that the case is really tight, and I don't know if it just didn't fit in quite right, but I was not able to get the machine to boot, this machine. I was not able to get it to boot properly. The light came on, but it didn't actually do anything. So I'm going to have to take it back out of the case, which is too bad because it looked really nice. But and it sounds really good. The fans work. So yeah, next week we'll see if we can, if I don't have time before that, we'll see if we can get back on that because GoCV is in desperate need of some of your GPU acceleration. So, speaking of GPU accelerations, so I have a challenge to my friends at Bedrock. Atención, Bedrock. Okay, so here's your challenge. So I just discovered this really awesome, let's see if we can find it in the news. Cow detection, OpenCV.
Cow detection. Wow.
Cow detection. So, OpenCV 2021. Let's see if I can find it. Here we go. All right. So, OpenCV's AI competition 2021 has been going on using a new depth sensor from Intel. And one of the coolest ones I found is this awesome demo showing tracking cows in a pasture.
We are in the perfect place for
We
this.
are in the perfect place. Yes, I got to put my mask on so we don't contaminate each other. So, oh, wait, we're not even looking at this. There we go. So this was the cow tracker that is being worked on by this French team, at least some of whom I think are Spanish from their last names. But I looked at this and I thought, if there was ever something that the team at Bedrock could more easily do, it is to produce a deep neural network that we can use. Basically, it can be done in Caffe, it could be done in TensorFlow, right? It could be using one of the existing networks and just retraining it and tailoring it. But we want this. We want to be able to take a sample of video. We want to be able to fly a drone over a field and have it recognize the cows.
Wow.
So that's our challenge. That's our project. That's our task. So let's do this.
Any restriction on what we have to choose?
It
as
has
a
to be.
platform?
It has to be
OpenCV?
something that we can integrate with OpenCV. So OpenCV has the ability, and if we could actually take a look at this. So if you were to look at GoCV, and we were to look at the docs, and we were to look down for the deep neural network capability, well, too fast, too far. Yeah, here we go. So in the API that's supported, we can, and there's some examples of this actually on the GoCV site, which it also needs to be redone. Actually, it's in the repo, sorry. I lied to you. So in the GitHub repo for GoCV, if you look at the commands, you'll see that there's actually a DNN detection example. There's also a Caffe classifier. So the classifier would be like if you wanted to hold the cow up in front of the camera and it says it's a cow versus it's a dog. The DNN detection is, I think, closer to what you would want in that it's actually using a tracking model so it's able to say where the cows are.
Okay.
So this is probably what you're going to need. And so you can take a look at it's got a SSD that's already been trained, and you could use that as a starting point. But yeah, all of this code is on the GoCV repo under commands, DNN detection. So your mission, cow detection.
Okay.
All right.
Absolutely.
Well, that's it.
Thank you very much.
So that's it, my friends. It's been fun, it's been real, and it's been real fun. So on that, I bid you a fond adios and see you next time. Computer.